In our last lesson, we learned about rules that we have for the sum and product of the roots of a quadratic. And today we're going to be extending that to cover polynomials of any degree. It sounds a little bit scary, but it's really, really not too bad. Before we get started, let's take a deep breath. And let's begin. So here we have effectively the formulas that will find us the sum and the product of the roots of a general polynomial, a polynomial of any degree. So we see here that the sum of the roots is going to be an minus 1, which is basically the second coefficient, divided by an, which is the leading coefficient, and then it's made negative. Okay. And it says that the product of the roots is going to be the last term, the constant term, divided by, again, the leading coefficient. And this time there's this negative 1 to the n factor that's in front of it. And I did a little bit of color coding here. I wanted you to see that there's a lot of similarity in the formulas for the sum of the roots between quadratic and degree n polynomials. You'll notice that both of them for the sum of the roots are the second coefficient, so b for the quadratic and a sub n minus 1 for the degree n polynomial. They're both that divided by the leading coefficient, so a in the case of the quadratic and a sub n in the case of the degree n polynomial. You'll notice that they both also have a negative in front of them. So the sum of the roots is always going to be the negative of the second coefficient divided by the first coefficient. In the case of the product of the roots, there's a little bit of a difference, but I hope to show you that it's actually not a difference. It's just you'll see. So the product of the roots is always the constant term divided by the first term, and the product of the roots over here is also the constant term divided by the first term, the leading coefficient. The difference is that this one has a negative 1 to the n, whereas this one doesn't. But I think what I would mention to you is, in the case of a quadratic, what is n? N is 2, right? So this might as well have a negative 1 squared on front of it. It doesn't matter because negative 1 squared just gives us 1, which means we stick with this relationship. In other words, these rules cover these ones. You could memorize just the degree n, and it would cover you for quadratic. The quadratic is just a specific case of the degree n polynomial. Now, in our previous lesson, we really looked at it, we sort of proved where these came from, and I want to do the same thing here. So the next thing that we're going to do is sort of show where these things come from, because I do think it's important for you to know where they come from. When we get to the sort of near the end of this video, we're going to talk specifically about cubics, and there's some extra special things that happen with cubics and quartics that we can sort of see through this. Okay, so now we're going to work on deriving the relationships for the sum and product of the roots of an nth degree polynomial. So we're going to start by considering a polynomial of degree n. So here it is, right? I'm just saying that the first coefficient is a sub n because it matches with x to the nth power. The next is a sub n minus 1 because it matches with the x that's to one lower power. It's going to go all the way down to a1 x to the first and a0. And then I'm going to note that the roots, I'm going to call them p1, p2, all the way up to pn. And it's important because of the fundamental theorem of algebra, I know that because this is nth degree, there should be n of these roots. That's why I labeled them p1 through pn. So any polynomial with these roots can be written in factored form as x minus p sub 1 times x minus p sub 2 times x minus p sub 3, and so on, all the way up to x minus p sub n. All right, now in theory, the next step is to like super duper mega FOIL this thing out. In theory, I need to multiply this entire thing out, and that's wild. But I sort of had that extra video that came at the end of yesterday's lesson about another perspective on how to multiply binomials. And in that, I talked about this idea that when you multiply this many binomials, what's really happening is you're looking for all of the different ways that you can pick one thing from each of these to multiply together. So if I was going to multiply all of these things together, I would first say, well, I could go through and I could pick x in every single one of these. If I picked x in every single one of them, if I did x times x times x times n, every one of them I picked the x, that would be x to the nth power plus. Okay, great, so I did that one. Now the next thing I could do is I'd say, what if I picked in x in every single one of them except for one of them? In one of them, I chose the p, right? So in this first one, I would get negative p sub 1, and then in all of the other ones, I would get x to the n minus 1, right? And then I could also do where I picked, negative p2, and I picked x in all of the other ones. That means that for n minus 1 of them, I would pick x. And I could do that for all of these, right? I would also have negative p sub 3 times x to the n minus 1, and I'd go all the way down until I had picked negative pn x to the n minus 1. Now, what's wild about this is, so I just did all of this work, and that was only for the next one of these terms. I have to do a whole lot. There's going to be sort of like a dot, dot, dot in the middle of this. And then the very, very, very last thing in my expansion, did you notice that my very first thing was where I picked x in all of them? The very, very, very last thing would be when I finally worked through all the possibilities, and the last thing I could do is I could pick not x in all of them. I could pick negative p1, negative p2, negative p3, negative p4, negative p5, all the way to negative pn. If you think about that, what that would be, and I'll sort of write it here, it would be negative p1, negative p2, negative p3, dot, 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 all the way to negative pn. And I know this is really messy, but give me a second here. I'm hoping that we'll be able to make sense of all of this, right? So the x to the n in the beginning, that makes enough sense. I hope we're okay with that one. So that's that, right? Let's make sense now of this part right here, right? All of these ones that have x n minus 1. You notice they're all negative? So I could effectively factor that negative out, and they're all also x n minus 1. If I factored the negative and the x n minus 1 out of all of them, don't I wind up with p1 plus p2 plus p3 plus dot, 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 all the way down to pn? Notice that this right here is the sum of all n roots, right? Now, let's sort of keep going with this, right? I mentioned that there was going to be this dot, dot, dot in the middle where all of these middle missing terms, I'm basically skipping all of these guys right here. And then I'm going to jump all the way to the end where I want to look at the constant term, this constant term right here. Look at what that is. It's every one of them has a negative with it. So don't I have n factors of negative 1? And then what's left after that is p1, p2, p3, all the way up to pn. Notice that this right here is the product of all n roots. So similar to what we did in the quadratic, by expanding this thing out like this, we're able to sort of see these things showing up. And when we go back and compare it to the original polynomial, to this thing that we said that this thing was supposed to be, we said that this thing should have been the same as a sub n x to the n plus a sub n minus 1 x n minus 1 plus dot, 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 all the way down to a0. So now, just like we did with the quadratic, we're going to go through and we're going to make sure that these coefficients match one another. If these two polynomials are going to be the same as one another, then sort of I need this coefficient to match this one, and all of these things are going to need to match up just like we did with the quadratic. So the first thing I want to do is there's nothing in front of this xn, so I need to move this one. So if I go through and multiply this whole thing by 1 over a sub n, then my polynomial becomes a n minus 1 x to the n minus 1 over a n plus dot, 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 plus a0 over a n. So now I've got this thing looking much more similar. This general polynomial is looking like this one that we had here. And so now I'm going to set these coefficients equal to one another. Right? So first let's work with those blue ones. Right? The blue ones that were the coefficient of the xn minus 1, I have negative p1 plus p2 plus dot, 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 plus pn. That has to equal an minus 1 over an. If I just multiply that negative over, I'll get that the sum of my roots, all n of those roots, is negative an minus 1 over an. And that's exactly what we said it was going to be before. That was our key point from previously. Now let's look at the constant term, all of this red over here, right? This constant term is supposed to match with this constant term, which means that negative 1 to the n times P1, P2, P3, all the way up to Pn, that has to match A0 over An. Okay? Well, now I just need to move this thing over, and I can do dividing and multiplying by -1 is the same thing. So I'm just going to sort of multiply this over so that it matches the same. P1, P2, up to Pn, the product of all of these roots has to equal -1 to the n a sub 0 over a sub n, which again is what we said that it was going to be in our previous key point. I know this was a really long derivation with a lot of letters in it. We're going to get into some examples now on how we actually use these facts, but I wanted you to see where this came from. It's really gonna pay off and help us when we're later talking about cubics. All right, so let's take a look at an example where we've got some numbers, and even some imaginary and complex numbers, yay. So consider a real quartic equation, here it is, and you're told that two of the roots are 3i and 1 minus 2i, and you're asked to find the values of a and b. Well, one of the things that we hopefully notice or remember is that the sum of our roots should be negative a over 1. So if I can figure out what the sum of the roots is, it should just be the opposite of the a value. Similarly, the product of the roots should be -1 to the n, which in this case is 4, times b over the leading coefficient, which is 1. So, I mean, great, this is just 1. The product of my roots is just going to be b. So now, if I just know what all the roots are, I'm set. Okay? So do I know all 4 roots? Well, I mean, kind of. They gave me 3i and they gave me 1 minus 2i, but they also gave me that this was a real quartic equation. Now, because it's real, what other roots do we have that go along with these? Don't we also have the complex conjugates? So negative 3i is also a root, and 1 plus 2i is a root. Now that I have all 1, 2, 3, 4 of these roots, I can go through and find the sum and the product. Right? So the sum of the roots will be 3i minus 3i plus 1 minus 2i plus 1 plus 2i. So neat thing happens, all the imaginary stuff here drops out, and I just get 2. That means that negative a has to equal 2, therefore a has to be negative 2. Yay, we're halfway done with this. Now the other thing we need to do is we need to look at the product of our roots. Okay, so let's consider that. Product of the roots. For the product of our roots, I've got to do 3i times negative 3i times 1 minus 2i times 1 plus 2i. Okay, well, let's see here. This is just negative 9i squared. And this one over here is 1 minus 4i squared. This is 9. This is 5, and so we get 45. Well, great, 45 has to equal b. Therefore, b has to be 45. And we're done. Now, I mentioned in the quadratic video, in theory, you could have done this problem by taking all 4 of these roots, turning all 4 of them into factors, then foiling all 4 of those factors together and getting this entire polynomial. But you're really sort of doing overkill on your work when we can use this process to pinpoint just finding a and b. I'm hopeful that after getting through that huge long derivation of where those things came from, that seeing a sort of concrete example like this gives you hope that this isn't that bad. This is something you can do. Okay, and then we get to this example that honestly looks a little bit scary, right? The equation 3x cubed minus 5x squared plus 2x minus 4 has roots p, q, and r. Okay, so it has 3 unknown roots, and they're asking us to find the value of p cubed, q squared, r squared, all of this stuff. If I try and read that out loud, I'm sure I'm going to make a mistake on some of those powers. They want me to find this thing, right? I want to remind you, problems that you're given in a class in the IB exam, they're designed to be solved. This is not some unsolvable problem, and your answer is supposed to be, haha, can't do it, this is too hard. This is something we can do, right? And so I want to point out to you that there's got to be something here that's about the product of the roots or the sum of the roots or something like that. So as you look at this, do you notice anything in common? Do you see anything that we can maybe work with? Maybe you notice that there's some common factors here. All of them have 2 powers of all 3 of the roots. So maybe I could factor that out. If I factored out p squared, q squared, r squared, what would be left? The first term would only have p, the second term would only have q, and the last term would only have r. Now that we know that what we're looking for is this problem might not be nearly as bad as we thought that it was. So I'd like you to pause the video here, see if you can recognize what this is and sort of what's being asked for, and see if you can figure out what that is from this problem. What I hope you notice is that this first thing right here, this is just PQR, the product of the roots, squared. And this thing here is just the sum of the roots. So let's sidestep over here and figure out what is the sum of the roots. According to the rule we learned earlier, it's supposed to be the opposite of the second term, -5, divided by the leading coefficient 3. In other words, the sum of the roots is 5/3. So this is 5/3. And the product of the roots, is supposed to be -1 raised to the n power, that's 3, times the constant term, -4, divided by the leading coefficient 3. So this thing here becomes -1. The -1 times the -4 gives me +4 divided by 3. So the product of my roots is 4/3 squared. So this is 16/9 times 5/3. This is 80/27. And we're done. Right? This ability to find relationships between the sum and the product of roots allows you to really access some sort of strange problems. And you can get at these answers really directly instead of having to figure out what the roots are and then compute this bizarre thing. There's a whole variety of questions that can be asked about this. So we're going to go through one more example here, and you'll see some more of them in the assignment this evening. All right, so I've got sort of one more example like this, and then we're going to move into one last sort of phase of the lesson. So now consider this polynomial here. Right? It's actually a polynomial equation. So how many roots does this polynomial have? Part A should be easy, particularly if you remember the lesson from a couple days ago. By the fundamental theorem of algebra, this thing has to have 5 roots. By the way, I've mentioned in the past sometimes like things that you can say in math to make yourself sound a little bit more official and fancy. One of them is the word let. You say, let x equals 5. Starting with by the and then quoting some result also makes you sound kind of fancy. So it's like, by the power of Grayskull, by the fundamental theorem of algebra, this must have 5 roots. It just gives you a complete sense that sort of makes it sound like you know what you're talking about, or that you like Shira. For part B, we want to find the average of the roots of this polynomial. And you're like, what? Like, we haven't studied how to find the average of the root. Like, this isn't something we've talked about. I'd encourage you to think, how do we generally find an average? Don't you add up all the things and divide by how many there were? Well, the question just asked how many roots it had. So this is saying find the average of the roots of this polynomial. Like, pause the video for a moment, see if you can think about how you're going to want to do this. Well, I guess what we're thinking is that we could do the sum of the roots and then divide it by how many roots there are. So how am I supposed to find the sum of the roots? The sum of my roots is supposed to be the second coefficient divided by the leading coefficient, and it's always supposed to be negative, which is 5. So this is 5 divided by 5, so the average of the roots of this polynomial is 1. You might be surprised how often, not all the time, but how often IB questions are like this. There's really not a ton of work to be done. You need to be able to read the question and understand what's being asked for, and then devise a way to get yourself through it. So I mentioned there was going to be one other type of sort of like weird question that's related to cubics and quartics. And it's a little bit of a fringe type of question. It's sort of a strange thing, but it's something where if you've seen it before and if you understand how it works, it's really easy to do, but it can often be sort of like a harder part of a problem. So it's good for us to have seen. So I want you to remember the beginning of the lesson where we spend like 8 minutes deriving the relationships for the general polynomials. I'm going to do that again for a cubic, but it's going to be cleaner this time, and I think it's going to be a lot clearer. So stay with me. I want us to consider a polynomial like ax cubed plus bx squared plus cx plus d. It's degree 3, which means it's going to have 3 roots. We're going to call them p, q, and r. My question is, does this coefficient c mean anything? We know that b is usually about the sum of the roots, and d is about the product of the roots. So what is c about? So I'd like to show you. So let's take a look here, right? So imagine that we've got these roots p, q, and r, right? P, q, and r, I could write this factored polynomial as x minus p, x minus q, and x minus r. And then I know the thing's going to want to have an a on the front, so let's go ahead and just throw an a out here because we're allowed to multiply by a constant. It's not going to change the result of the rest of this, right? Now I want to think about like super mega foiling this thing out, okay? And I mentioned previously that we can think about multiplying binomials as you picking one thing from each of these to multiply. So what I'm going to do here is I'm going to there's several different categories of what I could pick, right? I could pick x in all three of them. I could pick x in only two of them. I could pick x in only one of them, and I could not pick x in any of them. So I'm going to do this in 4 separate stages for how many x's I choose. All right, so choosing x all 3 times means I choose x and x and x. And then there's the a from the front. Okay, cool. So this is just going to be a x cubed. Nobody's surprised about that. That was supposed to be the first term anyway. Okay, choosing x 2 times. If I chose x twice, that would mean that I would have picked like negative p, actually choose a different color here, means I would have chosen negative p and then the 2 x's. So that would be negative px squared. Then I could have chosen negative q and the other 2 to be x's, that's negative qx squared. And then I could have chosen negative r and the other 2 x's. So that would have been negative rx squared. And again, we're not surprised about the, oh, also we have the a on this thing because of the a out front. And again, we're not surprised about this one. In this one, I could factor the negative and the x squared, and we have the a also, and we have our p plus q plus r. There's the sum of our roots, just like we thought. Okay, I'm going to jump down to the one at the very bottom because we've seen this one before too. We're gonna leave the choosing one x because that's the sort of new thing. Not choosing x at all. The only way to do that is to pick negative r, negative q, and negative p. So that's going to be my negative p, negative q, negative r, the a from the front. Again, we're not surprised about this one because this is negative 1 to the 3rd power, a p q r. Here we have our product of those roots, the way that we sort of expected that we would. What happens when I choose x only once, right? When I choose x only once, let's see here. If I chose x this time, what do I have to choose in the other two? Don't I have to choose q and r? So I'd have like q, r, x. Or I could choose this one here. If I chose that one to be x, what would I choose in the other ones? Wouldn't I choose negative p and negative r? So that would be plus prx. And if I chose x only in the third one, I'd have to choose p and q in these ones. That would be pqx. And remember, we still have that a from the front of the polynomial. What this thing represents is we have the a, we can factor out the x, and we have qr, pr, and pq. And what these are, if this was the sum of all of the roots and this was the product of all the roots, this is the sum of all of the ways that you can multiply together 2 of the roots. It's funny, you could think about this as the sum of all the ways you could multiply together 1 of the roots. This is the sum of all the ways you could multiply all 3 roots. And this is the sum of all the ways you could multiply 2 of the roots. So this c term, this c coefficient winds up being about these things. So there's sort of this other relationship that we can say that qr plus pr plus pq has to equal that c coefficient divided by a. Like I said, this is a really fringe kind of thing, and you're likely only to make sense of it if you sort of rederive this in the problem. I'm hoping that made sense. If it didn't, ask me some questions about it. I'm very, very much open to talking to you guys about this. I'm hoping to be able to bring you to an understanding of it. Let's try one last example where we see this. Consider a polynomial 5x cubed minus 20x squared plus 6x minus 17 equals 0 with the roots p, q, and r. And they want us to find the value of this thing. So if you're feeling up to it, pause the video and try this one. If you want me to walk you through it, we'll take a look at it now. Just like we did in one of the previous examples, you may notice that there's a common factor here. I can factor p, q, r out of all of them. When I factor out p, q, r, I'm left with pq plus pr plus qr. What I have here is the product of all the roots. Product of all roots. And what I have right here is I have the sum of the product of pairs of roots. Okay, and these are relationships that we've gotten before, that we've seen before. We know that we find the product of the roots by looking at the -1 to the third power, because it's degree 3, times the final constant coefficient divided by the leading coefficient. And this is 17/5. This one here, the sum of the product of the pairs of the roots, sorry, that's a complicated phrase right there, is, we had found that it was positive, this coefficient divided by the 5, so 6/5. This here simplifies to 102/5, and there it is. That's the value of this quantity. There's definitely a reason that I split this lesson into 2 parts, so one that was about quadratics and one that was about higher order things. You can see that there's a lot going into this. The solving of these problems is really not super complicated, but understanding where they come from takes some time and some energy. So I hope that you're willing to spend that time and energy and make sense of it. And like I said, if you've got questions, please let me know. I'm more than happy to help however I can. Best of luck as you work through these exercises and in all your learning.